Thanks for the introduction. Good morning, everyone. This is Lou from University of California, San Diego. I'm going to present our work on designing a fault-tolerant persistent memory programming library called Pangolin. Pangolin not only provides crash consistency, but also fault tolerance features for user space applications to handle persistent memory errors, including hardware uncorrectable ones and hardware undetectable errors. Persistent memory, or PMEM, has finally arrived. Intel has announced their Opt-in-DC persistent memory modules in April, so now you can buy them and install them alongside your DRAM DIMMs. Persistent memory is better addressable and cache coherent. When it's used as storage, a user space application can memory map a PMEM file and use load store instructions to access durable data without the page cache or file system code in the way. This provides the fastest path from user space to durable storage. And this access mode is termed direct access, or DAX. However, direct access brings challenges for programming. A widely recognized challenge is how to maintain crash consistency with the presence of volatile CPU caches and limited support for durable atomic stores from hardware instructions. A programmer has to carefully reason about when and in what order stores become persistent and implement transaction or recovery procedures to ensure data consistency in case of power failures. On the other hand, fault tolerance is equally important, but much less researched for persistent memory. Media errors, such as broken memory cells or bit flips, can cause data loss. Software errors, including buffer overruns or using dangling pointers, may also corrupt the data. Persistent memory DIMMs and their memory controllers implement some kind of a hardware-based error correction coding algorithm to detect some memory errors, similar to how ECC DRAMs work. According to whether memory errors are detectable or correctable by the hardware ECC, we can divide them into 3 different types, and they require different responses from the software. The first type of error is both detectable and correctable by the hardware ECC algorithm. In this case, the application will simply get good data without even knowing an error has happened. This requires no further processing from the software. If the error is detectable but not correctable by the ECC algorithm, the memory controller will raise the exception to the operating system, and the operating system isolates the page containing the error and sends a SIG bus to the application to notify it. Many applications are not ready to handle SIG bus, especially from persistent memory. The consequence is that many of them will crash, and they will lose data caused by the error. To repair this type of error, the application needs to handle SIG bus and use some source of backup to repair the corruption and overwrite the affected memory range. Then the persistent memory DIMMs will get repaired data and remap it to some good spare memory cells. The last type of error is not even detectable by the hardware ECC. They can be some media errors that accidentally escape the ECC check, or they can be some software-induced errors that are transparent to the memory controller. This type of error will result in corrupted data being delivered to the application. If the application does not have any software detection and a correction mechanism, it will consume the data and have unpredictable consequences. Therefore, from software perspective, it needs to be aware of uncorrectable and undetectable errors and handle them properly. This requires having some source of redundancy to repair corruption and implementing some software-based error detection and correction mechanism that works in addition to hardware ECC. You probably wonder, conventionally, we use file systems to provide protection for persistent data. Why not keep relying on them? Well, we know some file systems, for example, Nova, can provide protection for persistent memory data, but it can only do so through its read and write interface, where the data transfer is still managed by the file system. If the application memory maps the file, it essentially bypasses the file system. So if the file system code is not running, it's very difficult for it to protect memory-mapped persistent data. As a result, the application either has to handle all the error complications by itself, or we can design a persistent memory programming library to simplify this task. That gives us motivation to develop Pangolin. In Pangolin, we aim to both ensure crash consistency and also protect application data against media and software errors. Meanwhile, Pangolin aims to incur as low as possible storage overhead for providing fault tolerance. At the high level, Pangolin combines replication and parity as redundancy to repair corruption. A naive approach to replication is to simply duplicate all the data in a separate file. Apparently, this doubles the storage requirement for persistent memory. Instead, Pangolin only replicates its metadata in the object store, which consists of allocation bitmaps and transaction logs, and it uses parity to protect arbitrarily sized, randomly distributed object data. The metadata replication and object parity together only incur about 1% storage overhead for a gigabyte-sized object store. Pangolin checksums all its metadata and object data to detect hardware undetectable errors. When adding parity and checksums to an object store, a challenge comes up as how to maintain the consistency between related parts when modifying PMEM objects. In Pangolin, when an application wants to modify PMEM objects, we copy their data into DRAM-based object-level buffers. We call them microbuffers. The application can freely modify the buffered objects without concerning about the checksum or parity consistency. Later, when the transaction commits, Pangolin writes the modified objects back to their original locations and automatically refreshes their checksums and corresponding parity ranges in a fairly atomic way. In the remaining slides, I will first show how Pangolin organizes its data, and then I will explain some implementation details of the transaction mechanism. Pangolin creates an object store using memory-mapped persistent memory file. In such a mapping, Pangolin first reserves space for its metadata replication. Then it virtually divides all the data pages into equally sized rows. A row contains a set of pages that are continuous in address space, and the row size is 1% of a data zone size. Zone is a term we borrowed from libpmob to reference a huge memory block for object allocation. A zone size is 16 gigabytes in both libpmob and Pangolin. So Pangolin's row size is 160 megabytes. And for each data zone, Pangolin reserves one row as object parity. We call them rows because Pangolin views all the data pages of a data zone as a two-dimensional array, and it computes parity vertically across all the rows. That means a page from the parity row is the exclusive OR result of all the data pages of the same column. By doing this, we can afford losing one whole row of data and repair it using the parity row and other data rows of the same zone. We can also adjust the number of rows to make a trade-off between the storage overhead and the maximum amount of data we can repair. As mentioned, Pangolin introduces macrobuffering to provide transactions. When the application wants to modify a PMEM object, Pangolin creates its macrobuffer and transfers the object's data from PMEM to its buffer. In this process, Pangolin installs a signal handler to watch for SIGBUS and verifies the object's checksum to detect hardware undetectable errors. If it traps a signal or finds a checksum mismatch, Pangolin tries to repair the object or the page using the parity row and other data rows of the same data zone. If the data is good, or it's successfully repaired, the application can freely modify this object as it does in conventional DRAM programming. This animation shows the object modifies the range of object 1, highlighted by D1. The commit process of a Pangolin transaction consists of several ordered steps. First, it refreshes the object checksum in its macrobuffer. Then it logs both the updated checksum and the modified range using redo logging, and replicates all the log entries for protecting login data. After logging, Pangolin starts updating parity, which I will explain in the following slides. And finally, it writes the checksum and the modified range back to their original locations to complete the transaction. Although we only show a single object transaction here, Pangolin also supports multi-object transactions. And we have made the program interface very similar to what libpmob provides. Pangolin starts updating parity after transaction logging. For each modified range in a transaction, Pangolin first computes the XOR difference between a modified range in a macro buffer and the correspondingly unmodified range in PMEM to get a parity patch. Then it applies this parity patch to the corresponding parity range in the parity row. Pangolin does not have to read data from other data rows to update a range of parity. It views the modified checksum as one extra modified range of an object. So for cleanness, I'm not drawing the checksum or the replicated log entries from this slide. After parity updating, Pangolin updates the modified range to finish the transaction. In the current version of Pangolin, we do not log the parity change. If a power failure causes partial parity update, this can only happen after Pangolin has all the transaction logging, but before transaction completes. In this case, on restart, Pangolin first applies all the redo log entries to their corresponding objects, and then it reads data from all the data rows to recompute the affected parity range. For multi-threaded applications, Pangolin needs a way to coordinate parity updates if modified ranges share a segment of parity. This slide shows two threads concurrently executing two transactions, modifying object 1 and object 7 independently, but their modified ranges overlap in the column direction. So they share a range of parity. To update this range of parity, a straightforward method is to lock a parity range and serialize parity updates between threads. This works, but it sacrifices scalability. Alternatively, we can use atomic XOR instructions to update parity. Atomic XOR instruction can update up to 8 bytes of data atomically. Because parity words are independent of each other, as long as we can update each parity word independently, we can use atomic XOR instructions to update arbitrarily sized parity range in a lock-free way. However, the downside of atomic XOR instructions is that they can be slower than the regular ones or the vectorized version. So to get benefits of both words, Pangolin implements a hybrid scheme using both methods. It uses the modified range size to decide which method to use, and it uses shared mutex or redirect locks to coordinate both methods within a locked parity range. For small updates, for example, less than 8 kilobytes, threads can take the shared ownership of a parity range log and use atomic XOR instructions to update parity within this range concurrently. For updates larger than 8 kilobytes, a thread has to take exclusive logs of one or multiple parity ranges and use vectorized XOR instructions to get better performance. The threshold for switching methods is based on practical measurement, and it can vary between machines. We implement Pangolin on top of a libpmem and we compare it to both libpmem and its replicated version. We evaluate performance using a platform with Intel's OptInDC persistent memory modules. This figure shows transaction latencies for overwriting a single object of different sizes. The bars from left to right represent libpmem, its replicated version, and Pangolin. We observe that libpmem with replication not only doubles the storage requirement, but also often makes the performance more than twice worse. In Pangolin, its latency is 11% lower than libpmem with replication. We also evaluate Pangolin's performance using complex data structures that involve multiple objects. The two figures show average insertion and removal latencies for 6 mapping data structures. For these mapping data structures, Pangolin's performance is 90% of libpmem with replication. The reason for some lost performance is that some data structures are large, but a transaction only modifies a small part of it. In this case, Pangolin pays more for the data movement from PMEM to the macro buffer than it gains from overwriting a whole object, as the previous slide shows. Considering Pangolin uses much less space overhead for providing fault tolerance, and it provides object checksums to detect hardware undetectable errors, we consider this as a reasonable performance trade-off. In conclusion, we believe persistent memory programming libraries should also consider fault tolerance for critical applications, and we have developed Pangolin as a response. With Pangolin, we found that parity-based redundancy can provide similar performance compared to replication, and meanwhile significantly reduce the storage requirement. We also observed that microbuffering-based transactions can both support crash consistency and also provide fault tolerance for emerging PMEM applications. That's all my talk. Thanks for listening, and I'm glad to take any questions.
Okay, let me start the questions. So you explained that how Pangolin is going to handle the two different threads, try to modify the different object, right? How the Pangolin handles that if the two different threads try to access and modify the same object? Is the micro buffer is going to be shared?
So our micro buffer by default it's thread local. So if two threads, so it supports modifying different objects. So if threads have to modify the same object, they have to manage concurrency explicitly. So we do not support transparently modifying the same object. So it's the same limitation as in the PMEM, because two transactions modifying the same, the overlapping range can cause some inconsistency if one commits but the other fails.
I wonder what size transactions were you thinking that this was for?
Can you repeat again?
What size transactions were you contemplating that this would be used for?
What size of transaction?
Yeah, what size object would typically be updated?
Oh, it can be any size as long as the allocator supports.
So for very small transactions, do you know if the Intel transactional memory support runs on this hardware? And did you compare that with what you did?
Intel's transactional memory, right? So that it doesn't work out of the box for transactional memory because that works at cache level. So it doesn't handle persistence. So you can modify a cache line using that transaction instructions, but it doesn't guarantee crash consistency. So there are some related works talking about how to make that work together with persistent memory. So in our work, we don't use that to do transactions, but we do use that to optimize some implementation. For example, we use the hardware lock elision to do the read-write lock to optimize that, just to avoid taking the locks in some optimistic cases.
And I don't know the technology. Is there any significant wear in this memory, or wear is not a factor?
You mean wearing out?
Yeah.
We don't have data yet, but my guess is because it's much denser media, so writing wearing out can be a problem for this device.
So I wondered if wear could be an issue, then the parity area is going to wear much faster.
Oh,
than
that
the rest.
parity area. This is a valid concern. So we assume the memory controller and the persistent memory DIMMs will have some hardware-based variability mechanism. So they will remap things around to avoid overly writing the same range.
Okay, if there is no other questions, let's thanks to speaker once again.